Welcome back. For this second part, as promised, we're going to look at the proof of the theorem, a simple graph has a spanning tree if and only if it's connected. Perhaps the crucial piece here is the if and only if part of this statement. That means we have two directions to complete for the proof. The first, we will assume the hypothesis. Suppose that G is a simple graph that has a subtree. The goal will be to prove the conclusion that it is connected. For the second half of this proof, we will assume the conclusion. Let us assume that G is a connected simple graph, and the goal will be to prove the hypothesis that the graph G has a spanning tree. So, starting with the necessary conditions, let us suppose that G is a simple graph with a spanning subtree T. Remember what it means to be a spanning subtree. In particular, by definition of spanning subtree, it is a subgraph of the original graph G that contains all the vertices of G and is a tree. By definition, a tree is connected. Since it contains all the vertices, it means that G must also be connected. So that takes care of one half of the proof. For the other direction, let us suppose that G is a connected simple graph. We want to show that a spanning tree exists. Following the lead of the book, what you want to do is sort of consecutively identify a cycle and then remove one of the edges of that cycle or circuit. Because when you remove the edge of a circuit, the graph you have remains connected. It does not change the characteristic of connectivity by removing a cycle edge. So if you do that for the first cycle you find, you've decreased your graph by one edge, and then you look for another cycle, do it again, until no circuits or cycles remain. Now, since the original graph was connected, removing these edges again preserves the connectivity, which means at the end, you end up with a graph that's connected on all the vertices of G, but contains no circuits. That means the resulting graph is a tree. It happens to be a tree that contains all the vertices of G, which means it is a spanning tree. And with that, we have proven the theorem. The next step will be to answer the question, how do we construct spanning trees? And the first answer is to do the very naive process of removing edges from circuits until no circuits remain on the graph. This is exactly what we did in the previous proof. The difficulty with this is that you need to be able to detect cycles in your graph. On small graphs, it's pretty easy. On big graphs, it can be difficult. So it is not really the most efficient way to go about creating spanning trees. Instead, we're going to choose to build the tree up in clever ways. I think you may be familiar with these from your data structures classes: depth first search and breadth first search of graphs.